All right, welcome back, Calc BC students. Sorry I have to be a little quiet. I'm in the hotel room and it's late, and I don't want to keep other people up. Anyway, so let's just look at parametric equations part 2. So let's say we have a parametric equation. X is a function of time, so the position in the x direction, comma, position in the y direction is equal to t cubed, comma, sine of t. So that means that the x position is t cubed, time cubed, and y position is sine of t. And this is in meters for time greater or equal to 0 seconds. Okay, now if I wanted to get this into rectangular coordinates, again the procedure is I know that x is equal to t cubed, and so I solve for time. So t would be equal to the cubed root of x. And then I put this into my y equation, so y is equal to sine of t, and so y is a function of x would be equal to sine, and then t is x to the 1/3. And so if I graph this out, and I have y as a function of x, let's see, the graph looks something like this. Okay, so what we want to do is I want information about this graph. So I want to find slope, slope of the local tangent lines. I want to find extrema, and I also want to find concavity. But unfortunately, when you're looking at physics problems, you're really in the realm of time. And so having y as a function of x is really not terribly practical. So we want to stick with time, but we want to be able to analyze the graph of y versus x, which is actually the two-dimensional path of this particular particle. So what we're going to do is come back over here, and one of the things I'm going to show you first of all is that with parametric equations, let's say I want to find the velocity components. So the velocity components are just x prime of t, comma y prime of t, which is equal to the velocity in the x direction as a function of time, comma, the velocity in the y direction as a function of time. And so all I need to do is to look at each of my positions, and then just differentiate each with respect to time separately. So my velocity components are going to be the derivative of t cubed is 3t squared, and the derivative of sine of t is cosine of t. So this gives me my velocity components in meters per second. And we'll see why that's useful in a moment. But again, I want information about the graph of y as a function of x. But again, I want to stay in the realm of time. So the first piece of information that I want to look for is for dy dx. Now if I go over to my graph over here, dy dx at any point is going to be the slope of the local tangent line. So at any point, let's say point here, dy dx is going to be the slope of the local tangent line, and I can also use that information to figure out what my critical points are by setting my first derivative equal to 0. But again, I want to be in the realm of time, not in the realm of y and x. So the first derivative is relatively easy because I can divide the top and bottom by dt, and I get that dy dx is dy dt over dx dt. And if I do that, then this is equal to y prime of t over x prime of t, which I can also write as the y component of velocity as a function of time divided by the x component of velocity as a function of time. So now what I can do is I can get my local tangent line slope and still stay in the realm of time. So for example, if we look at the above parametric equation, then x is t cubed and the y component is sine of t. And so my dy dx is going to be equal to dy dt over dx dt. And so all I need to do is get the pen working, and I get dy dx is equal to dy dt, or y prime of t, or if you prefer, the y component of velocity, which was the derivative, the derivative of the y component, which was cosine. So I can write this as cosine of t divided by the x component of velocity, which is 3t squared. And so this gives me all the information I need to figure out at a particular time whether the graph of the path of the particle is increasing or decreasing. I can also set this equal to 0 and figure out where my extrema points lie. I can also, I could use the first or second derivative test to figure out what type of extrema they are. And so this gives us information about this particular graph, y is a function of x, but in terms of time, which is a lot more practical. Now, one that's a little more confusing is if I want to find the second derivative of y with respect to x. And again, this gives you the concavity, and it can also be used to test whether you have a local minimum or maximum once you know the critical points by setting dy dx equal to 0. So the second derivative is going to be equal to the derivative with respect to x of dy dx. Now here's where this is a little bit confusing, because I want this still to be in the realm of time. And so what I'm going to do is I'm actually going to divide top and bottom here by dt. And so I'm going to divide this d by dt and this dx by dt. And if I do so, then I get d dt, so the derivative with respect to time of dy dx, all over, here I've got this term here, and all over dx dt. Okay, so this is a little bit confusing. So let's go through this example. So my second derivative of y with respect to x, which again gives me the concavity intervals of the particle path on y versus x, is going to be equal to, okay, let's take this piece by piece. So the first is the derivative of time, derivative with respect to time of dy dx. So that's going to be equal to the derivative with respect to time of dy dx. And dy dx I can get from up here. So that's the derivative with respect to time of cosine of t over 3t squared. And then that's all divided by dx dt again. And dx dt is going to be the derivative of the x position, which is also the velocity component in the x direction, which in this case is 3t squared. Okay, so now on the top, I'm going to have to use the quotient rule. And so I've got, let's see, the derivative of the first, so that's minus sine of t, times the second, which is 3t squared, minus the first times the derivative of the second, all over this one right here, 3t squared squared, all divided by this 3t squared. And so we have to be a little bit careful here. But you can factor this out and simplify. But basically, this gives you the second derivative as a function of time. So we've stayed in the time realm, and that gives us some very useful information about this graph up here. And you would use the first and second derivative like you normally would. Usually, like on the AP test and on the homework problems I gave you, you'll ask things like, is the function increasing or decreasing at this time? So you put the time in and you see whether this is positive or negative. Another thing could be asked for is if there's points of extrema or horizontal tangent lines, where you set this equal to 0 and solve for time. The second derivative, again, gives you information about the concavity of the graph of y versus x, and can also be used to help test for extrema. Okay, so when we come back, oh no, actually, let's do one more thing. So in your homework problems, there's also parametric equations where you have x and y as a function of theta. So for example, let's say I have x as a function of theta, comma y as a function of theta. and that would look something like 3 sine of theta, comma, let's say cosine of theta. And they will ask you questions, and they'll ask you questions, for example, of finding dy dx, and they'll give you some curve, and I'm not sure exactly what this curve looks like, but let's say it looks something like this. So you want to find the derivative. Then you kind of use the same rule. So dy dx would be dy d theta over dx d theta. And then the second derivative would be equal to d theta of dy dx over dx d theta. So similar to the last one. For this one, this is really kind of practice for getting into polar coordinates, which we'll do later. So don't worry about that too much now, and just kind of go through the exercise, because we'll be using this later in 10.4, section 10.4, but you don't have to actually worry about the meaning of this quite yet. Okay, so in the next video, we'll come back and do all of the physics equations.